convection, we're interested firstly in the question, will it actually occur? And then the related question is, when will it occur? The trace shown here is rather interesting. There is, as you can see, a maximum surface temperature which gives us the dry adiabat up which parcels will ascend, and then a mean mixing ratio line which is calculated by mixing the lowest 50 hectopascals, which is saying the updrafts sample a layer of air feeding into them. Those two lines intersect at a point on the trace where the environmental lapse rate is equal to a saturated adiabat, the same lapse rate at which the parcels will cool. And so, in other words, the CAPE is equal to 0. There's no energy available to drive convection. There's an equilibrium level at about 300 hectopascals, which is 30,000 feet, and there's a level of free convection at about 9,000 feet. Remember, for that area bounded by the equilibrium level and the level of free convection, there's a positive area between the environmental virtual temperature profile and the parcel virtual temperature profile. But also on this trace, there's a region where the energy is negative. That is, an ascending parcel is cooler than its environment. We want to get parcels to the level of free convection for convection to begin, and so the energy that's required to lift a parcel from the surface to the level of free convection is known as the convective inhibition. That's illustrated in the schematic on the right. Firstly, you see in the inset how we calculate a level of free convection. Typically, it's by having a surface temperature and a dry adiabat up which parcels will ascend, and the mean mixing ratio for the lowest 50 hectopascals. You can see in the trace that there's a green area, a positive area between the level of free convection and the equilibrium level, otherwise known as the level of zero buoyancy, but then the red area represents the convective inhibition, the energy needed to release the CAPE. You can overcome kinetic inhibition by large-scale lifting. You simply lift parcels to the level of free convection, or you can erode the SIN either by heating the surface, so you can see how that would minimize that area, or by increasing the moisture, or indeed a combination of the two. And there's the equation for convective inhibition. It's the integral of the equation we've seen earlier for CAPE, only now we're integrating between the surface pressure and the pressure at the level of free convection. Here's some model output. On the left-hand side, you can see a distribution of CAPE, getting up to values around 2,500 joules per kilogram. And then on the right-hand side, you can see the convective inhibition, and some of the values are quite large. So if convective inhibition is too large, then it doesn't matter how much CAPE you have, you simply won't realize it because there's too much energy required to overcome. Whereas the lower the value of the convective inhibition, the more likely it is that heating or lifting or moistening of the profile will actually allow the CAPE to be realized with parcels reaching the level of free convection.